Hey, welcome back, Marauders. This is section 3.4, and it's on the ideal gas law. It's my favorite section, so let's get started. The ideal gas law helps us relate the pressure, the volume, the number of moles, and the temperature of a gas. All four of these variables, they affect each other, so if you change the pressure, it's going to affect something else, one of these other three variables. If you change the temperature, it has to affect one of these other three variables. And so the ideal gas law looks at the relationship between these variables and helps us calculate and solve for them. So first of all, the pressure of a gas is caused by the particles being in constant motion and having collisions with the side of the container. And so if they're having frequent collisions with the side of the container, if they're having collisions with a lot of force with the sides of the container, then you have a lot of pressure. Pressure can be measured a few different ways. It can be measured in ATMs, probably the most common way. 1 ATM or atmosphere is the normal pressure that we feel with just the atmospheric gases pushing on us. We don't really notice it because we're always experiencing 1 atm of pressure. It's also equivalent to 760 millimeters of mercury, 760 torr, or 101.3 kilopascals. And so you can use conversion factors to convert between any of those units. Make sure you label the units and make sure you pay attention to what units they're given in each problem. Temperature is how much kinetic energy the particles have, so it's how fast they're moving and how much energy they have because they're in constant motion. If you heat a gas, the particles start moving faster and have more kinetic energy. And so temperature can be measured a lot of different ways. We usually measure it in Celsius, but whenever you're doing anything with a gas, you need to measure it in Kelvin. It's a pretty easy conversion. You're just going to take the temperature in Celsius and add 273 to get the temperature in Kelvin. Kelvin, it uses that number 273 because then 0 degrees Kelvin is absolute zero, and that's when the gas particles will stop moving. They won't be moving around at all anymore. And therefore, we never have negative values of temperature in the Kelvin scale. So make sure anytime you're doing a problem with gases, you make sure that the temperature is in Kelvin. And if it's given in Celsius, convert it by adding 273. So there's some relationships between the variables that we'll look at first. The first one's Boyle's law, and it's the relationship between pressure and volume, and that's an inverse relationship. And so it can be shown in this little diagram right here. When we decrease the volume, when we go from here to here, when we push down with this piston, then the pressure is going to increase. These particles now have less space between them. They're going to collide with the sides of the container more frequently, and you'll have a higher pressure. So pressure and volume are inversely related. That means when one of the variables goes up, the other has to go down. Charles' law is the relationship between volume and temperature. And the volume and temperature relationship is a direct relationship. When one goes up, the other will also go up. You can see that in this graph right here. If you increase the temperature, the volume is going to go up. The gas is going to expand. And so it can be shown here when the gas is cold, the particles are kind of close together. But when you heat them, they start moving around more rapidly, bouncing off the sides of the container and increasing the volume. So that's a direct relationship. Avogadro's law shows the relationship between volume and number of particles. You can experience this law like if you add air to a balloon. When you're blowing up a balloon, the balloon gets larger. It gets larger because you're putting more gas particles into the balloon. So it's a direct relationship. As you add more gas, the volume increases. So if we take all of those gas laws and put them together into one equation that includes pressure, volume, number of moles, and temperature, we get the ideal gas equation. This one's super important because anytime we know three of these variables, we can solve for the fourth. The ideal gas equation also has this other letter in it, R, and R is the gas constant. So the gas constant, it can be found on the back of your periodic table, and the value we're going to use most frequently is 0.0821 liters times ATMs over moles degrees Kelvin. There's some other gas constants as well. They have different units, so you want to pay attention to the units and make sure that the units match up with the units in the rest of your problem. This is good to know right here that at standard temperature and pressure, which is 0 degrees Celsius and 1 atm, 1 mole of any kind of gas is going to have a volume of 22.4 liters. You can solve that by plugging the values into PV is equal to nRT, putting in 1 atm, solving for the volume, putting in 1 mole, and putting in a temperature of 273 Kelvin. And if you put in those, you'll get a volume of 22.4 liters. But since this is kind of a standard, it's useful to know that, and then sometimes you can save yourself from doing the calculation. It's also important to know that this works for all gases. It doesn't matter what the identity of the gas is. This works for hydrogen, it works for helium, it works for carbon dioxide, it works for oxygen gas. It works for all gases that behave ideally. All right, so let's take a look at an example. Let's say we had a 4.3 liter tank and it holds 14.3 grams of helium at 45 degrees Celsius. What's the pressure in that tank? So when I get a question like this, what I like to do is write down all the given information first. So we were given the volume, the amount of gas, and the temperature. I'm going to write those out and write out the units. And then I see that I need to solve for pressure. So anytime you have three of these things and you want to solve for the fourth, you know it's going to be a problem where we use the ideal gas equation. All right, so the amount of gas was given in grams, and we know to put it into the ideal gas equation, it needs to be in number of moles. So the first thing I'm going to do is I'm going to convert that 14.3 grams of helium into moles using the molar mass of helium. So the molar mass of helium from the periodic table, 4 grams per mole. So we convert and we get moles of helium. Temperature was given to us in Celsius. So we're going to add 273 to get the temperature in Kelvin. Now that we have everything converted into the correct units, now we can plug everything into PV is equal to nRT. And so we'll plug everything in. So I've got the pressure is what we're trying to solve for. We've got the volume. We've got the number of moles. We've got the gas constant. I included the units here, liters times ATMs over moles degree Kelvin. It's important to include those so that you can see that they're going to cancel out with everything else that you're putting into the problem. And then here is our temperature. And so now I'm just going to use algebra and solve for the pressure. So I'm going to multiply all these and divide by 4.3. And when I do that, I get 21.6 ATMs. So using PV is equal to nRT is pretty easy. It's just plugging in the values, using algebra to solve. The main thing you need to pay attention to is first, before you plug things in, make sure all the units are going to match up with the units of the gas constant. All right, let's take a look at one more. So if we have a 2.5 liter flask containing carbon dioxide at 35 degrees Celsius and 1200 torr, how many grams of CO2 does it contain? All right, so same thing I did last time. I'm going to write out what's given in the problem. We were given the pressure, the volume, and the temperature. We're going to try to solve for the number of moles. Again, you can tell it's an ideal gas equation question because we have three of the variables. We're going to solve for the fourth. So torr, that's not normally the units of pressure that I want to use. I want it to be in ATMs so that it matches up with the gas constant and can be canceled out. So to convert that, I'm going to use the conversion factor that 1 ATM is equal to 760 torr. The torr will cancel out, and I get ATMs as my units of pressure now. Temperature, just like always, we want to add 273 to get the temperature in Kelvin, and there it is, 308 degrees Kelvin. So now I can plug everything into PV is equal to nRT. I'm going to be trying to solve for N this time. So I plugged in the pressure, the volume, the gas constant, including the units to make sure it cancels out with everything, and then there's my temperature. I'm going to solve for N, so I'll multiply the pressure and the volume together. I'll divide by R, and I'll divide by the temperature. And when I do that, I get 0.156 moles of carbon dioxide. This problem has one more step after that because it's not asking us for moles of carbon dioxide, it's asking us for grams. And the ideal gas equation will just give it to us in the number of particles in terms of moles. But we do know how to convert from moles back into grams. We're going to use the molar mass. So I found the molar mass of carbon dioxide on the periodic table. It's 44 grams per mole. And then I'm going to multiply by that 44 grams per mole so that the moles cancel out. And I get 6.87 grams of CO2.